Hello everyone, welcome to COMP-162. The topic of today's lecture is computer architecture. In this lecture, we are going to learn about the conceptual model of a computer system. We are going to see a real world physical product of the computer system. We are going to take a look at different components of a computer system and see what their functionalities are and focus on the main processing block in this system, which is CPU, and see how a simple mathematical operation is performed within this processing engine. This is the conceptual model or architecture of a computer system. As shown here in this figure, we have the CPU, which stands for Central Processing Unit. We have I/O devices such as keyboard and display or computer screen. We have RAM, and also we have the system storage. All these different components are connected together via a bus system. What is a bus in a computer system? In a computer system, the bus is a simplified way for many components and devices in a computer system to communicate with each other. If you want to make an analogy in real life with the bus system in a computer system, we can refer to highways, where highways connect different locations or different cities to each other, but bus system connect different components within a computer system to each other. The carriers in highways are cars and automobiles and trucks, and in computer system, the carriers on the bus are data and information. Let's take a look at a simple example in here and see what is happening in the bus when two different devices or components in a computer system would like to communicate with each other. Assume here that the CPU wants to know if a user typed anything on the keyboard. The first thing that CPU does to do this task is to create a message and send that message over the bus. So the message contains of two things. The first thing is the destination or the receiver that would like to communicate with. And the second part is the question or the request that it has. For example, here, since it wants to know if something has been typed on the keyboard, the receiver is going to be the keyboard. And the message or the request is did the user type anything on the keyboard? So it sent this message over the bus. And in here, all components connected to the bus are going to receive this message, including the keyboard and the display or the monitor. So the message is keyboard, did the user type anything? Since the keyboard and display both are connected to the bus, we'll receive the message and they can take a look at the message and see the content of the message. So they both read the message. So the keyboard sees that, okay, the recipient is keyboard, so it takes the message in, but the display sees that it is not on that call, so it simply discard the message. Keyboard read the message and respond to CPU. So it creates a message like this. It put the CPU as a recipient of the message and put its response in the second part by saying that, yes, user typed A. So this message again gonna go over the bus. So every component connected to the bus going to receive this message. Since the CPU is the recipient of this message, it reads it and sees that the message from the keyboard and understand that the user typed A. So it grabbed A and probably gonna store it in one of its temporary registers. Display also received the message, but since it's not a recipient of this message from the keyboard, it simply discards that message. Before proceeding further into the conceptual model of a computer architecture, let's take a look at the real world physical product of a computer system and see the different components within that system. Some of you might be familiar with this picture. This picture shows a motherboard of an IBM uh, PC that has the 386 processor integrated within this motherboard. This motherboard in a computer system installed within the tower of the desktop, and all those peripheral like monitors, printers, keyboard are connected to this motherboard within the computer tower. Okay, so the first and the main component of this motherboard is the CPU. In here, we don't see the CPU, we only see the socket of this CPU, which is a Pentium CPU. So basically the chipset of the CPU is going to sit on this part, which has many pins in it. So this is the older version of IBM PC. So the newer version has different peripheral and I/O connected to them, and the CPU has more pins integrated within it. Okay, the second component within this motherboard is the RAM slots. So as you can see here, the RAM are shown within this blue rectangle. So these are the slots that RAM is going to be placed on it. So this motherboard has RAM technology of type D. So it's a dynamic RAM, or the acronym is DRAM. And after 1993, we had newer technology for RAM, which called STRAMs, or synchronous DRAM. And then the newer version and technology for these RAMs are double data rate SDRAM, or in short, we call them DDR SDRAM. As you can see in here, there is a chipset which called North Bridge, and the main component, the main functionality of this North Bridge chipset is to coordinate access to main memory for the CPU and the peripherals. The next component within this motherboard are the I/O device slots. So these slots are shown in blue again in here in the motherboard. So as you can see, we have four slots over here, and so this is the first one, second one, third one, and fourth one. And we have different technology of the slots over here. So this called PSI. So these black one are the ISA slots. And also, as you can see from here, we have the built-in I/O that they're used to be connected to our input-output peripherals like our printer, our network cable, and the keyboard. So the keyboard previously used RS-232 serial port, and that's the port for that. And also we have South Bridge chipset over here that this chipset facilitates input-output device communication with the CPU and with the main memory here. The other component on the motherboards are storage connectors. These storage connectors that are shown in here, they are used to connect to storage devices such as hard drive and floppy disk. So there are different standards for the storage connectors. So we have old standards that called parallel ATA, and the newer standard has different technology. So the older version was SCSI, and the newer version is serial ATA. Here in this picture, we are seeing the newer version of the motherboard used in computer desktop. As you can see here, our I/O devices are located in here. Still, we have PCI, we have AGP, and then we have our South Bridge and North Bridge. We have the CPU socket, we have the uh, RAM, RAM slot, and also we have our I/O connector at this end of the board. We also have USB headers integrated within the motherboard, and also some other I/O peripheral. Now let's go back to our conceptual model of a computer architecture. So we explained how two different components within a computer system can communicate using bus. In here, we have CPU as our main processing engine, and RAM, which stands for random access memory or memory of a computer system. So we talked about CPU a bit. Now let's talk about the functionality of the RAM and see how its internal structure is and how the capacity of a RAM depend on the number of lines in the address bus. This figure shows a block diagram of a typical RAM, and we can see the input to this RAM and the output from this RAM. As you can see here, one of the input to this RAM are the address bus. We have the address bus, we have the data input or wires for the data to get into the RAM, And also we have a pin called write. So when this pin is enabled, the RAM is ready to receive the data or write the data within itself. So the address will tell the RAM which location within the RAM the data should be written to. So one thing to note that is the number of the lines or wires within the address bus tells us the capacity, the maximum capacity that RAM could have. So if your address bus consists of 20 wire or 20 pin or 20 bits, then your memory capacity is 2 to the power of that number of bits. So in this case, 2 to the power of 20 or 1 megabyte. And then we have our data output pin. So when we want to read from this RAM, we simply send 0 to this pin. This means that we want to read. And then we enable the address pin over here, telling the RAM which location from the RAM we would like to read the data from. And as soon as we do that, then the data is going to be automatically placed on the output of this RAM and placed on the bus, data bus of the system. RAM is one of the crucial components of the computer overall architecture. When we talk about the memory of a computer, most often we are talking about its RAM. RAM capacity can significantly impact the processing speed of a computer system. So there are two different types of information that can be stored within RAM. So the first type are instruction code of a program that they are stored within RAM sequentially. So when a CPU wants to execute a program, fetch those instruction code sequentially one by one from RAM and execute each one after another. So the second type of information are data values or variables, information such as text, images, and videos. These type of information can be stored within RAM, anywhere within RAM, and they are not necessarily needed to be stored sequentially. So both instruction and data within RAM can be accessed using addresses. We talked about RAM, and now at this point, let's take a closer look at the CPU. The CPU is the brain of the computer system. It is the part that actually executes the instruction. Let's take a look at inside.
Memory registers are an important part of the CPU. They can be considered as a temporary memory and they are much faster than external memory. When the CPU executes instructions, it uses these memory registers as a temporary storage. So it's fetch the instruction from the RAM or data from the RAM loaded to these registers, perform the operation on the data and store that data back into the registers, and then um, send the data from these registers to the RAM.
CPU also consists of a unit called arithmetic logic unit, and which the short form is ALU. This component is responsible for doing basic arithmetic or logic operation on values that stored in the registers within the CPU. The arithmetic and logic operation example that we can name are addition, subtraction, multiplication, or XOR and NOT. Instruction register is another important register within the CPU that holds the current instruction that is currently being processed by the CPU. Another key important register within the CPU is instruction pointer registers that hold the address of the current instruction which is stored in the RAM. Another important component of a CPU is the control unit. As the name implies, the control unit is responsible for controlling the data flow within the CPU. The control unit is like a state machine. So let's see how the control unit works. The control unit state machine has very simple structure. It consists of three states. The first state is fetch, second is execute, and third one is the repeat. In the fetch states, control unit has the RAM to send the instruction and store that instruction in instruction registers. In the second state, it executes these instructions. There are only a small number of possible instructions for the CPU. And the third state is the repeat state, where it adds 1 to the address stored in the instruction pointer and go back to step 1. Here is the graph of our state machine or the control unit state machine. As we mentioned, it consists of three simple states. State 1 is fetch, the second one is execute, and the third one is the repeat state. In the fetch state, it fetches the instruction from the RAM, and then it executes that instruction. That execution could be add instruction, could be load instruction, or some other instruction, subtract instruction, multiplication instruction, or go to instruction, or store instruction. Depending on what the instruction is, the CPU is going to execute that instruction. So once done that, it goes to this state. In this state, it's going to add the value 1 to the instruction pointer and then go back to the fetch instruction, where at this point, going to fetch the next instruction of our program that is stored in the RAM. To explain this concept, let's go through a simple program. For this program, we assume that we want to add two variables that are stored in the memory, which we call variable A and variable B. So basically, variable A and B point into the memory location which contains some data. For us, assume that data are some integers like 2, and then for B also that variable contain a number 3. So what we want to do is to add these two variables together and store the result into variable C within the memory. So the program that we write to do this process consists of three instructions. The first instruction is the load instruction. Basically, you load the value of variable A into register R1. The next one is that you load the value of B to register R3. And after you load those values, now you are able to add them together. Then you add these two variables and store the results to register R2 within the CPU. So once you have the result within the CPU, now take that result and store that result into location C within the memory. So to summarize, we have these 4 instructions, and this is CPU want to execute this program for us. Let's see how the CPU does it. Let me explain this block diagram briefly before going to describe the CPU processing sequence for this program. Okay, here is our memory. So as we mentioned earlier, the memory can store data value and instruction. As you can see from here, we assume that the first part of the memory uh, is the place that we store the data, and the second part of the memory is the place that we store the instruction. So our program right now is loaded into the memory. You can see the four of our instruction are stored within the RAM, and the address of this instruction is given in here: 2005, 2006, 7, and 8. We have 4 instructions, and our data also um, specified by variable A and B. Basically, these are the address uh, that contain those data value for us. So A and B and C are address or variable. So in high level language, we call them variable. And in assembly, basically, these variables are uh, the pointer that referring to a location within the memory. So for us now, A is pointing to a memory location that contains value 2, and mm, B is the pointer that point to the memory location with a data value of 3. And now C is actually a variable that's pointing to the memory location that right now at this point um, uh, uh, contains a value of 1. All right. So now that we know our memory map, let's take a look at the CPU. So this is basically our CPU that interacts with the memory. Okay. So the first instruction is the load instruction. We said that instruction registers contain the current instruction that being executed by the CPU, and the instruction pointer is a register that point to the address of that instruction within the memory. So basically, to start, the instruction pointer point into the location that need the instruction to be fetched. So IP instruction pointer now point to 2005. Therefore, CPU goes in here and then fetch that instruction into the instruction registers. Once it has the instruction uh, in the instruction register, it take a look at the instruction and start doing the operation as specified in this instruction register. So for this first instruction, what it does, it load the value of A to register R1. So value of A is in here. It takes the number 2, which is the content of that register, and then put it in register R1. In the next step, uh, instruction pointer is going to be incremented by 1. Now instruction pointer is 2006. Therefore, it points to this location within the memory. So it points to this location, and therefore in the fetch states, the CPU is going to fetch this instruction and put it in the instruction register. Now this instruction tells the CPU to load the value of B into the register R3. Therefore, as you can see here, the value of 3 is stored in register R3 within the CPU. What happened next is the repeat instruction. We basically, at the repeat instruction, we increment the instruction pointer by 1. Therefore, the value is going to be 2007. Now we are at this point in the memory. Therefore, the CPU is going to fetch that instruction, put it in the instruction registers, take a look at that instruction register, and start processing according to this instruction as specified in this instruction. Then CPU need to add these two registers together. Therefore, an arithmetic operation has to be done. Therefore, CPU uses the ALU to do that, and once it's done that, it's going to store that value into register R3. Now, again, we are at the state of the repeat. In this state, again, the IP register going to be incremented by 1. Now it's pointing to 2008 location in the memory, and then therefore it's fetch this instruction, put it in the instruction register, take a look at that value. It's right now say store the value of R2 back into the memory location C. Therefore, it takes this value and put it in the memory location C in here. And since the value is 5, therefore this value 5 is going to be written within the memory. So now the process is completed and the value of 5 has been written into the memory. Let's come back to our conceptual model of a computer architecture and summarize what we have learned in this lecture. As we said, the RAM is the computer main memory. This is where the program and data are stored. The CPU goes in a never-ending cycle, reading instructions from RAM and executing them one after another. This cycle of reading instruction from memory and execution is orchestrated by the control unit within the CPU. The CPU simply look at the instruction pointer, see where it is pointing, read the instruction there from the RAM and execute it. To execute an instruction, the control unit uses the ALU plus memory and or the memory registers within the CPU. This concludes Lecture 1, Part 1. In Lecture 1, Part 2, we are going to learn more about the assembly language framework and concept. See you then.